Please understand that alternating currents cannot be directly used up. Like, you can't have a fluctuating voltage. So you need to have a DC equivalent, right? That DC equivalent, let's say if I were to talk about current, and this wave is my alternating current wave, I can never use it. Let's say, for example, if you were to charge a phone, the phone would keep charging, discharging. For the first part of the cycle, it keeps charging. And then for the next part, it keeps discharging. And that would completely destroy my equipment. So we need to work on a DC equivalent value. And we can work that off using the formula RMS, where RMS is the DC equivalent of the AC supply. RMS means root mean square. This is your peak voltage, the I naught value divided by under root 2. So that is what our point is, that alternating currents can be easily produced on a large scale using the phenomenon of electromagnetic induction. They can be stepped up or stepped down using transformers, definitely. They can be transmitted over long distances using high voltage transmission. But for household purposes, as the voltage is reduced, the corresponding current increases. And to withstand this high current, thick cables must be used, which increases the cost of installation. Since the current and voltage fluctuates continuously, therefore calculations involving power are difficult to compute. So to overcome this, engineers have designed a technique called the RMS value. RMS value stands for root mean square for current or voltage, right? And it is simply the DC equivalent for an AC supply. So if for current, I have an RMS value I naught upon under root 2, and for voltage, I have an RMS value of V naught upon under root 2, and you were to work off RMS for power, you could simply multiply the two values. Please understand that under root 2 multiplied by under root 2 would give you just 2. Right? And therefore, we can say that RMS for power could be somewhat this. Right? For an AC supply, the experimental observation concludes that the current, voltage, and power are given by the following equations, which is this, and this. Since the AC current is changing, we can't use it. How to calculate RMS values for current, voltage in case of a symmetrical square wave? A symmetrical square wave somewhat looks like this. What you simply do is you will square this value, right? If I were to work it off for this, I will square the value. Squaring the value would make this 36, and this would also become 36, right? 6 is for T half. So it becomes somewhat like 36 for T half. And when you square minus 6, that is for the next T half, which also becomes 36. And your wave somewhat becomes, your wave graph converts into this value. If you are to work off the value, you can simply check it off. You need RMS, right? RMS means root mean square, right? Your mean would be the average of this wave. The average is 36 T divided by the time for the entire complete cycle, right? And from here, you could get your answer as 6 amperes. If you were to get a value for a non-symmetric square wave, right? Your graph is somewhat like this. You square this, this becomes 81 for T half part. This is T half. And minus 4 when squared becomes 16 for the next T half part. So T half would make it T, right? 81 multiplied by T half and 16 multiplied by the next T half divided by the total time, which is T, would give you 48.5. This is mean average, mean or the average, right? The total area divided by the total time. And you simply underroot this value to get the RMS value, which is approximately 7 ampere. In some cases, they give you an equation, right? By the way, this equation, like this equation can be written somewhat like this. This V is at a specific instant, anytime value. V naught is the peak voltage. If you were to draw a graph of this, let's say it's a sine wave. So this 20 is actually your amplitude, right? You were asked to calculate the RMS. So 20 divided by under root 2 would give you the RMS value, right? If you were asked the mean value, you need to understand that it is a symmetrical wave. So that cancels off. Whatever is for the first part is also for the next part, right? So V mean is 0, right? Suggest why power is produced although V mean is 0. Now, based on the fact that V square upon R, power is proportional to V square and not V, right? Although mean value of the voltage is 0, V square is positive. Do you understand the fact that mean would simply mean, let's say if this is T half, this is T half. I'm not using root mean square, I'm just using mean. That would actually be the fact that 20T plus minus 20T upon 2, sorry, T upon 2. Don't you think these two cancel off because it's a symmetric wave? Had it been root mean square, you would have squared this value, you would have squared this value for the T half part and then underroot it to get RMS. I'm not using RMS right now. And for, by the way, alternating currents, we use RMS using this formula. So we don't need to do that. I hope you understand why the V mean is 0 here, because it's a symmetrical wave. Please do not confuse V mean with VRMS. Root mean square is different, mean is different. So based on P is equals to V square upon R, power is proportional to V square and not V. Although mean value is 0, V square would always be positive because squaring the wave would simply establish the fact that the negative value also becomes positive. And therefore power is always non-zero. If R is equals to 20 ohms, calculate P max. For P max, you need to have the peak voltage. That is the maximum voltage that could be produced, which is 20. So V naught squared divided by R, which gave me 20 watts. Calculate PRMS. For PRMS, you just simply divide by 2, and therefore you get the value of 10 watts. You are asked for the frequency of the AC supply.
Sir, 2Q.
Please understand from simple harmonic that this is sine omega t, right? I've written the formula here as well. Omega is equals to 2 pi f. 2 pi f could be equated to 50 because omega is 50 from this entire equation here. And simply divide it off to get the value of the frequency. Moving forward, calculate how the P max changes if the frequency of the supply is doubled. Now, P naught, the P max value is P naught, by the way. Depends on V naught and R. Now, both the factors are independent of the frequency. Voltage is dependent on work done and charge. Resistance is dependent on voltage and current. Both of these are not dependent on the frequency, therefore P naught remains unchanged. Right? Let's say I have an AC supply, VRMS value of 10 volts, frequency of 10 hertz. Y sensitivity is 4 volts per division, time base is 5 milliseconds per division. Right? Let's say they're saying sketch the waveform observed on the CRO screen. Please understand that Y sensitivity is 4 volt per division. You can simply work off the value for the V naught. Since it's an AC supply, right? VRMS is equals to V naught upon under root 2. You multiply RMS value, which is 10 by under root 2, you'll get a value of 14.1 volts. If you use 3.5 divisions, if you multiply 4 by 3.5, you'll get approximately this value, 14.1 volt. Right? You're provided with a frequency which is 50 hertz. Right? Frequency can be worked out. The time period can be worked out from the frequency such that time period is equal to 1 upon frequency. And you'll get 20 milliseconds. So 20 milliseconds is for one complete wave to be formed, or you could say 0.02 seconds. Your time base is 5 volts per division. I am simply dividing this to understand the fact that you need 4 divisions to form a wave. 1 division, 2 division, 3 division, 4 division. Now this is one complete wave. Right? You are also given a single diode here. So you need to understand that the diode will cancel off this entire wave. And hence there is nothing observed here. Diode will allow one part of the voltage to pass through, which is, let's say, if this is positive, this is negative, current would flow. However, AC supply keeps on shifting poles. So when this becomes positive and that becomes negative, it will not allow the voltage to pass through. Now, for another occasion, the graph observed is somewhat like this, right? Your R is 1.5 kilovolt. They're asking you to calculate the mean voltage. Now, you need to understand that this is one part of the wave, and that is the other part of the wave. Right? After rectification, I allow my wave to look somewhat like this, and when I connect it to a capacitor, the capacitor will smooth it, thereby cancelling this part, and the wave looks somewhat like this. Right? Your peak voltage was 6, and हो जाएगा यार वो simply V mean is simply the addition of 2 divided by the time interval in between, the maximum and the minimum value divided by the time interval in between. So you get the mean voltage. They're asking you the mean current using a single capacitor discharge. V is equals to IR. You know for a fact that for a wave like this, you'd prefer using the voltage value, which is a stable value for your calculations. And that is why I use the V mean value. Your resistance was 1.5 kilo ohms. You could convert this such that 1.5 into 10 to the power of 3, and therefore your current works out to be 3.3 milliamperes. Now they're asking you, you have the current, they're asking you calculate the charge which flows through a single discharge, right? A single discharge is from this time interval to this time interval. You subtract the time to get the discharge time, which is 12 milliseconds, right? 12 milliseconds, and you have 3.3 milliamperes, and you'll somewhat get your charge content to be 40 microcoulombs. They are further asking you to calculate the capacitance of the capacitor. Q is equals to CV, and the voltage value where the capacitor is discharging comes out to be C, the discharge. Capacitor is used for the discharge purpose, right? And discharge is during this cycle 6 and 4. And that is why I've subtracted the two values. Moving forward, you have a magnetic field of 10 millitesla. Current placed in a magnetic field creates a magnetic force, right? A wire AB is positioned on a chemical balance as shown. When no current flows through the wire, the balance reaches 40 grams. Meaning to say a wire is put on a top pan balance, you could say, which reads off a value for the mass. The direct current of 5 ampere is now switched. Now when there's a current moving, the current will have a magnetic force. Now you need to understand that the current flows in the direction of A to B. Right? Calculate the new balance reading. You need to understand that Fleming's left-hand rule is used to calculate the or work of the direction of the magnetic force. Using Fleming's left-hand rule, your first finger points in the direction of the field, the green lines, right? Your second finger moves in the direction of the current, and you will realize that the thumb, which is the magnetic force, points upwards, which tells you that the magnetic force is upwards, right? You will work off the value of the magnetic force, which comes out to be 0.1 Newton. The magnetic force is in the upward direction. The weight of the wire is in the downward direction. So technically you will subtract the two values. Weight of the wire approximately comes out to be 10 grams, right? I'm assuming G to be approximately 10 meter per second squared for my ease of calculation. Magnetic force of 0.1 Newton would give you 10 grams, right? It was mentioned in the question that the wire had a reading of 40 grams initially. Since weight and magnetic force are in the opposite directions, you will subtract them to get your new value. So the values will keep on fluctuating. If it's an AC current, the DC of 5 ampere is now replaced with an alternating current of RMS value 5 ampere. Calculate the maximum range. Now for RMS values, you need to understand that there are plus values and there are minus values, right? There's a positive cycle and there is a negative cycle. You're calculating an RMS value, right? And using F is equals to BIL, you can actually work off the value of the force. I'm using plus minus because there is a positive part attached to the cycle. There is also a negative part attached to the cycle, right? Simply giving me a force value, and the force would be divided by F is equals to mg, right? So if you need to work on the mass, you could further divide this value to get your value of the mass. By the way, this is in grams. Okay. Your maximum range would be 40 grams plus 10 under root 2, 40 grams minus 10 under root 2. And if you were asked about the variation, this value minus this value would simply give you 20 under root 2 as your variation. And if you were to plot a graph, it would come out to be somewhat like this. Next, chapter is quantum physics. It starts off with photoelectric effect. Now, what exactly is photoelectric effect? A scientist, Einstein, used an experiment, right, in which he developed a photocell. What exactly is a photocell? There's a metal connected to the poles of a battery, right? When this metal has a certain frequency incident upon it, or you could say when there is light energy being given out to the metal, right, at a certain frequency, it was noticed that the metals started to emit electrons. And when the metal started to emit electrons, there was a current witnessed. Right. This current, because it was being developed due to the presence of light, it was termed as the photo current. Photo as in light. Okay. Before we move on, you need to understand what exactly is the electron volt. You know for a fact that voltage is equals to work done upon charge, right? Now, work, if I am using voltage of a 1 volt voltage, and a charge of 1 E, where E is the charge value for an electron, which is 1.6 into 10 to the power of minus 19. And if I were to multiply these two values, right, don't you think you'd get somewhat 1 volt multiplied by 1 E would give you 1 EV? This is the electron volt. In quantum physics, we use electron volt as a substitute unit for energy. You need to understand that 1 electron volt is equals to 1.6 into 10 to the power of minus 19 joules. Similarly, 1 MeV is equals to 1.6 into 10 to the power of minus 13. Mega is into 10 to the power of 6. So that decreases, or basically increases the value by a power of 6. Right? So this is what I've mentioned here. Electron volt is an alternate unit for energy. It is defined as the amount of kinetic energy gained by an electron if it accelerates from rest through a potential difference of 1 volt. Let's say I have two plates, 0 volts and 1 volt. The work done between the plates is defined as voltage. Voltage is equal to work done upon charge, right? Work done could be replaced with kinetic energy. And simply you could work out that the kinetic energy is 1.6 into 10 to the power of minus 19, which is 1 EV, right? There's a particle called photon, which can be assumed to be a packet of energy, or could be a particle which has energy, right? It is believed that electromagnetic radiations consist of photons. A photon is defined as a packet of electromagnetic radiation which possesses a fixed amount of energy. This energy of a photon could be worked out using the equation E is equals to hf, frequency V is equals to f lambda. You know for a fact that electromagnetic radiations have a constant speed which is 3 into 10 to the power of 8 meter per second, and therefore this formula can be substituted as hc upon lambda, where E is the energy of the photon in joules, C is the speed of light, lambda is the wavelength of electromagnetic radiation, F is the frequency, H is the constant known as the Planck's constant, which is 6.63 into 10 to the power of minus 34 joule second. Let's say, for example, you had red light and you were asked to calculate the energy of a photon. Now, you know from AS that red light has a wavelength of 700 nanometers. Simply putting it in the equation, the Planck's constant is given to you in the data booklet. HC, C is this speed of light, which is 3 into 10 to the power of 8 meter per second, dividing it by the wavelength would give me the value of this amount in joules. And sometimes the examiner will ask you to convert it. So you simply divide this value by 1.6 into 10 to the power of minus 19 to get an electron volt value. Right? Now, photoelectric emission, as I mentioned before, was an experiment done to check if there was a photocurrent being produced or not, right? A simple photocell somewhat looks like this. The cell was connected to the negative pole and therefore termed as the cathode, whereas the collector was connected to the positive pole of the battery. And now light of a certain frequency was incident upon the metal plate, right? And it was noticed that at a certain frequency or a certain wavelength of the photon, there was emission of electrons witnessed. The ammeter started to give a reading value, and therefore photocurrent came into existence.